Good afternoon, everyone. So today's class, we have derived all of these math in the last week. So today's class, we're going to try to get an intuitive feel for what's going on, and then we'll do a quick demo and verify whatever we have in our board matches with what comes out in the hardware. And once we're done with that, we might be out of time, but if we have a little bit of time, then we can get a head start for induction motor, which we'll complete in the next 3 lectures. Okay. So today's class, what we want to do is basically address the last problem of the homework, which is to get this equivalent, per phase equivalent steady state circuit. So, per phase. Equivalent steady state circuit. So this is the final form we want to get into. And we are starting with a 3-phase motor. Right? So we have 3 individual voltage sources applied on each of those phases. And the only requirement is that these voltage be balanced so that the motor currents are balanced. The equations that we have derived so far, none of them require the currents to be assumed, the voltage to be assumed to be balanced. Right? We derived for generic currents, generic voltages, but going forward, we are going to assume the voltage is phase shifted by 2 pi by 3, and then the magnitudes are all constant, right? For the steady state equivalent circuit. So we have our voltages, and then again, each of those windings are a bunch of copper coils. So they're all going to have some resistance. And the winding distribution density is the same for all of them. It's just phase shifted by 2 pi by 3. So the total length of the coil would be the same for all of them. So the resistance is expected to be the same. The next component that we wanted to figure out to complete the circuit is the inductance that comes, the magnetizing inductance, which basically comes from when you pass a current through one of these coils. If you pass a current through one of these coils, it's going to set up a B field in the air gap. And we already saw the expression for the B field, dA of theta to be mu naught NSP I divided by LG times I think cos of theta, right? Yeah. For a two-pole case, if it was p-pole case, there will be p by 2 times cos of p by 2 times theta. And to set up this magnetic field, there had to be some current, and then with the associated magnetic field that comes out of it, there's going to be some energy, and we derive the inductance based on that energy method. We looked at energy at every single point in the air gap, right? And then used our energy density formula and integrated over the full volume of the air gap, going from 0 to 2 pi, and we got half Li square equivalent, whatever that was, and we got an energy expression for our inductance without this 2 by p factor. Then we looked at the second way of deriving the same thing using the method of flux linkage, which is far more powerful because the energy equation doesn't tell you anything about what happens when the other coil carries current, what will be the effect on this primary coil. Right? It complicates the picture a little bit. You can again find out the B field due to this, B field due to this, find out the energy, but it will be hard to decompose the energy of itself versus the energy it's contributing to the other coil. So we went with the flux linkage method, where what we did is we basically figured out what the B field is in the air gap and how much the B field links its own coils, A-phase coils, at every single incremental angle. We took a tiny incremental angle and we found out the number of conductors there, some Dn, multiplied by the flux that was passing through that loop, and then integrate the whole thing over on full cycle, and we ended up with the inductance. Right? And we did this for every single pole pair. So if we had a 2-pole motor, this would just be 2 by p, and we'll match up with whatever value we got from the energy method. But when you have multiple pole pairs, you have the option of either connecting them in series or connecting them in parallels. Or when you go to like say 8 poles, you have multiple options. You can have 2 of them in series, 2 of them in series, and then they combine 2 in parallel. Right? So the options are numerous. If you were to connect all of those coils in parallel, then whatever this factor is, you would multiply by another 2 by pi. If you connect them in series, you would multiply by p by 2. Alright, it's basically just paralleling inductors or series inductors. So the net inductance is just going to be a factor of it. And when I say I'm paralleling or series, I'm not paralleling or series the phase coils. Right? Each of these phase coils have within themselves n number of poles, some p number of poles. Alright, so what I'm paralleling is the the coils within each phase. I'm not paralleling coils across 3 different phases. That wouldn't be possible because we have 3 different voltage sources. Right? So when I say parallel, it's the phase pole pairs that I'm paralleling. Right? And then we figured out what the flux linking this A-phase coil due to its own current is going to be. And we got some L self times IA. L self expression is what we have there. And again, if I've asked the question that these coils are in series, then whatever is in the formula, you'll multiply by p by 2. If you put it in parallel, you'll multiply by 2 by p. So the inductance will change depending on the connection you're making. And then what we saw is if we start to pass current in the B phase, then there is going to be some flux that the B field that's set up by the current in the B phase, which is then going to link again with the A phase coil because these are all wound on the same core. So we looked at the example we had in our midterm where we had a core like this and a second core like this. So if this is carrying some current IA, this is carrying some current IB. If let's say this is initially 0, if this is creating some flux phi B, this flux will link into the coil, A phase coil, to produce some flux linkage, whatever this turns as Na times phi B. And then the d by dt of the flux linkage will give you the EMF across the coil. So other coils will also influence the primary coil. So that's the same thing we're doing here. Due to currents in the B phase, there is going to be coupling into the A phase coil, and the flux in that winding is going to be, we derived the formula again. It came out to be negative 1 by 2 L self times IV. So what this means is, if you end up providing, and the same we can do for C phase current as well, you'll get the negative same 1 by 2 times L self times IC. What this means is if you end up passing same current in all the three coils, same 5 ampere, 5 ampere, 5 ampere with no phase shift, let's say, then of course the sum of these three would end up being 0, which we already know because we pass DC currents in all the three phase coils. We know that the flux will be completely 0 in the area. So the math also bears out the fact. But again, this is not, the equation appears as if it's B phase current is subtracting the flux away from the A phase. That is not what would happen because if the A phase current is peak, when we pass three phase current, the B phase current would be negative half of it. Right? So this will become a positive term, this will become a positive term, and it will add up with this term to give you the 3 by 2 factor that we have here when you have all of these three combined together. Right? So when you have all the three currents passing in the coil, the net flux is going to be the sum of the three flux linkages, which is going to be this expression that we have here. This itself, IV plus IC, can we save the answer last time? That is going to be negative IA. So we ended up with the formula 3 by 2 times times IA. Somewhat quite surprising and obvious at the same time because we have three currents flowing in three different coils, but all of this information falls into just one single current at the end of the day. So the total flux linking the A phase coil is all embedded within the one single current information. That's because of the characteristic of the three-phase system that we set up. We set up the voltage to be 2 pi by 3 phase shifted and the another voltage to be 4 pi by 3 phase shifted. So the currents will also follow the same characteristic. And then in a three-wire system, there is no option but the sum of the three currents to be 0. Right? So it just ends up having coming out that way. And this is true whether we are looking at steady state or transient. It doesn't matter whether your circuit is in transient or steady state. It will always be 3 by 2 times L self times IA because this IA plus IB plus IC equal to 0 is true in transient as well as in steady state because it's a three-wire system, current can't go anywhere else. Right? Everybody clear so far? Okay. So let's fill up this part of the circuit. So we have some inductance, L cell, L cell, L cell, and then current IA going into this, IB going into this, IC going into this. How do I represent this cross coupling term? Where there is a flux linking the A phase due to currents in the B phase. How do I represent in the circuit? So whatever I've drawn here, that only represents this portion of it. Right? L cell times IA. Because IA times L cell will be the flux linking the coil. And if I differentiate d by dt, that will give me a L di by dt, that will be the voltage across it. Right? How do I model the effect of the B phase current on the A phase and C phase current on the A phase? Yep, Juno.
Would you use a transformer?
Transformer? Is there a much simpler way of doing it? Transformer is the right way if you want to do it, but there's a much simpler way.
The game block?
What was it?
The game block?
Gain block with a factor of
2.
3 over 2. Just scale this value by 3 by 2. Because that has embedded all the information. That's what is captured in this bottom equation here. Just a factor of taking the current and having a multiplication of 3 by 2. So that beautifully simplifies this circuit. Right? If you had to put like a transformer block, we cannot reduce it into a single phase equivalent circuit at the end of the day. Because you cannot ignore the current, even at steady state, you cannot ignore the current in the B phase because the B phase current would have an effect on the A phase. But it happens so that in a three-wire system, that sum of the 3 is 0, so it's just a factor of 3 by 2 times, and we can just model it as 3 by 2 times L cell. So this part is the magnetizing inductance diagram. In the book, it's called per-phase magnetizing inductance. Per-phase magnetizing inductance. Well, the whenever most textbooks just call it magnetizing inductance, drop the term per phase. The per phase is a very nice way of thinking about it because all the effect of when we go from a three-phase circuit to an equivalent one-phase circuit, basically we are capturing all the information of this three-phase at steady state using a single-phase circuit. Right? So this the LM is basically doing the same thing. All the information of the other two phases are being captured in the single LM. Right? The cross-coupling terms are all being captured. So there's a nice term used in the book, but most textbooks don't use it. Right? Okay, so far we have looked at there's actually a much easier way of getting the same expression. So let's say if you think of this as a solenoid coil and you pass some current through this, and the B field due to this is in this direction, BA. If you have another solenoid coil like this and you have a flux B field due to this being BB there, then you can resolve it into two components. One is in the vertical direction, one is in the horizontal direction. What will be the component along the horizontal direction? Let's say the B field there is BB. What will be the horizontal component? You can think of the angles, find the cos, sine, and figure it out, but there's much easier way. Again, the equations already have the answers right there. We know from this equation that lambda A due to IB is going to basically subtract out whatever this flux is. It is going to be a negative half of that flux in effect. Okay, that's what the term is ending up coming out to. So this would be, so this angle is 120. So you can do the math of it and figure it out too. So cos of 160, that will end up being negative 1 by 2 BB. And then the vertical one would be root 3 by 2 BB. And then BB itself is a function of current IB, right? Times some inductance value, whatever. And similarly, you can do for the C phase as well. You will end up with again x-axis projection, y-axis projection. You will end up with negative 1 by 2 BC. And then negative root 3 by 2 BC. So these two vertical components would cancel out with the correct current combination at time, let's say t equal to 0. A phase is along this peak. Right? If you look at the three-phase current at time t equal to 0, this would be our A phase. Then our B and C would be the negative half, negative half. So this and this magnitude would be exactly the same. These two would cancel out. This would be negative 1 by 2, negative 1 by 2, but the negative component makes it positive. 1 by 4, 1 by 4, and adds on to give you 3 by 2 factor. So this is a very useful tool. This happens to be so because of the way our winding was wound in a sinusoidally wound motor, sinusoidally distributed winding. You get this nice way where you don't have to go through the process of deriving the equation all over again. Just diagrammatically, you can visualize these inductor coils and exactly figure out what the contribution of this flux would be to this flux. Alright, it's just a pure property of sinusoidal distribution of winding. If you had some other kind of distributed windings, it won't happen that way. Alright, many textbooks use this as a way to derive it, but that's not the way to derive it. It's just a happy coincidence that it comes out in this nice way. But for different distributed windings, it will be a completely different profile. So if I ask you a question, let's say instead of a three-phase motor, I had a two-phase motor. Again, sinusoidally distributed winding. Let's say A phase is here. For a two-phase motor, where will the second coil be? What will be the angle for the second coil in a two-phase motor? During 90 degree or 180 degree? 90 degree. So this is your second coil. So let's say lambda A due to IA is equal to some L self times IA. What will be lambda A due to IB? Due to current in the B phase coil, what will be the flux linking the A phase coil?
What's E zero?
0, why?
Because they're offset by 90 degrees.
Perfect. So basically all the flux, again, the diagrammatic version that we saw there, all the flux due to this will be vertical in direction. Right? In reality, it will be sinusoidally distributed. Half of it will couple in the positive B field, half of it will couple in the negative B field, effectively making it appear as if it's all vertical component without anything linking along the horizontal coil that we have there. So this is just 0 times IB. So for any set of windings, let's say you have some coil, A phase here, and some other coil, some X phase at some angle theta. lambda A due to IA is going to be L self times IA, and lambda A due to some current Ix in a coil phase shifted by some angle theta is going to be cos of theta times L self times Ix. Okay. So we derived it for the case where the windings were 120-degree phase shifted in our lecture, and this cos of 120 ended up coming out to be -1/2, and that's how we have -1/2 times L self. If you have 90-degree, that will end up being 0. If you have some other angle, that will end up being cos of theta times L self. So this is kind of a precursor to what happened in an induction motor. In case of a permanent magnet synchronous motor, there are only 3 sets of windings, and all of these are fixed to the stator. In case of an induction motor, there are windings on the rotor as well, and those windings are rotating. So when they rotate, you can think of this as a coil with theta changing. Right? So this you can think of as a rotor coil. This is a stator coil which is fixed. So the rotor coil theta keeps changing. So the inductance on the rotor will actually keep changing. The coupling between the stator and the rotor will keep changing as the rotor starts to rotate. Right? So again, you can do this for any set of coil. Only if the windings are sinusoidally distributed. Otherwise, this would not hold true. Okay. So we have, going back to our expression, we have this term. So far, we only looked at, we have assumed the case that the ion is ideal, that it has infinite permeability, that all the flux will prefer the pathway going through the ion. But in reality, ion is not going to be infinitely permeable. Flux will prefer, and as you go to higher and higher currents, the core will start to saturate. So in addition to the pathway where the flux goes through the ion, there's also going to be flux that does not go through the ion, but closes the pathway through the air gap itself. Right? So the problem is this flux which is going through the ion, that is going to link to the other coils. But the flux that leaks out and closes the pathway through the air gap, that is not going to link through the other phase coils. Right? So that is not going to contribute. So whatever flux this term is, phi b, that is contributing to the flux linking due to current A linking into lambda A. But there is a component that leaks away that is not linking to this, and that won't contribute to the system. Right? So again, here if you have currents in the A phase, it is going to set a flux which goes across the core and links to the other coil. And it's also going to have flux component which is going to leak out and not couple with the other coil. So we're going to introduce another term for that. So this is lambda A due to Lm, which couples to other coils, L self times Ia. And in addition, there is something that leaks out, which we are going to call leakage LL times Ia. Right? This LL term does not couple to other phases. It only stays within its own phase. Right? So because of the flux just leaking into the air gap and not going through the ion core to link the other coil. So there is, in addition to the self-inductance, there is also a leakage inductance. Everybody clear so far? Okay. So the way we represent that, just another inductance LL for each of the phase, because each of the phase coil is going to have its own leakage. Right? So this is going to have its own LL, B phase will have its own LL, C phase will have its own LL. So this leakage is its own LL. This leakage causes its own LL. Right? Will there be a 3/2 factor to that as well? No, absolutely not, because these are only components that are flux of their own coil, they don't link to the other coil. If they did link to the other coil, the 3/2 factor would have come and it would become magnetizing inductance. This is purely leakage inductance. So the way I have drawn this, it would appear as if in addition to our self-magnetizing inductance, there is an added leakage inductance that somehow increases the net inductance. That is not what would happen in reality, because there is some flux that's going to be generated. A portion of the flux goes through the iron core and a portion of it leaks out. So when we derived this inductance equation, this was for the ideal motor where all the flux was only in the iron core, nothing in the air gap. Right? So when we go to a practical motor where some portion of the flux leaks out, it would be whatever this we derive, some portion of it would be reduced, that will be the net magnetizing inductance LL. Right? And then the remaining portion of it would be the leakage component that comes out of it. So in the homework, you can, when I told you to take the leakage inductance LL to be 10% of the magnetizing inductance, you would have ideally chosen 90% for this, 10% for this. But if you chose 100% for this, 10% for this, that's absolutely fine too. Why? Because there's a caveat as to how I define magnetizing inductance. It could either be this formula or it can be from measurement. Right? So since I didn't make that clear, either choice I will leave it to be correct. Yes,
so just to clarify that, so you're saying you would derive that self-inductance like normally, and then you just, like if it's 10% leakage inductance, you just reduce it by 10%.
Yeah.
Okay.
Yeah. So this whatever we derive, because this magnetizing inductance in itself, we have this nice expression. But if you look at the practical motor, like a common magnet synchronous motor that you would use in a regular drive, you would see that at zero current, you might have like some inductance of 30 millihenry or something. That's pretty high, like 5 or 10 millihenry. And let's say 10 millihenry. As the current goes to rated current, the inductance would plummet to like around 3 or 4 millihenry. It can plummet as much as like 60%. Because the core starts to saturate quite a bit. And once the core starts to saturate, this inductance goes down while the leakage inductance starts to creep up. Right? Because more and more flux would prefer the pathway of the air gap rather than going to the IR because they both know it's pretty much the same once the core starts to saturate. So it's a fine balance. So even when we operate this motor again for simulations and ideal scenarios, we assume this to be a constant, but in reality, as this goes down, this term starts to creep up. Okay. Any questions? Okay. So this is our inductance path. So next part, we will derive this EMF equation. I've left it to you as homework. I derived the torque in class, but the derivation for EMF is extremely simple. Whatever you did to derive the flux linkage in the A phase, you use the same procedure. So when you did the flux linkage lambda A due to IB, right, we looked at the number of turns of coil of A phase coil, NSA of theta. And then we use the flux coming from the B phase, so flux of the B phase coil. Now, instead, by doing the back EMF, we are going to be doing the same thing. We need to get the flux linkage first, and then once you have the flux linkage, how can you get the back EMF? Let's say I give you the flux linkage of the A phase coil. How do you figure out the back EMF of the A phase coil? What's the relationship between flux and EMF? Let's start there. Yeah, please.
E equals N d phi dt.
And d phi dt, perfect. So E equal to, let's leave the negative sign out for now, but it will become critical in a minute. N times d phi by dt, I'm taking the n phi inside. The n phi is our flux linkage lambda, d lambda by dt. So if I give you the flux linkage, basically to get the back EMF, you will have to differentiate the flux linkage, right? Now there are two flux linkages here, so we have to be quite careful. So there is one flux linkage right here due to the currents that we passed in the motor. Due to currents going in the stator winding, it created a flux in the air gap, magnetic field in the air gap, which then links with its own coil, causing some effect, which is going to have some voltage drop across it, which is what is captured by this inductance we have here. So if you have a current flowing through this inductor, sinusoidally varying current, it is going to have some voltage drop across it, which is what is being exactly captured by d lambda. If you differentiate the total, d lambda A by dt, that will be exactly the same as whatever voltage you capture across this term right here. Right? Now there's going to be another magnetic field in the air gap due to the rotor magnets. Alright, so think of it as two separate magnetic fields. One magnetic field due to the stator windings, and then there is another magnetic field which is being created due to the rotor magnet. And this again, we looked at it last class, how we shape it such that at some portions it's very small air gap. Farther we go out, the air gap is larger, and we can make use of the BH curve, where if there is a larger air gap, then the load line would go way down. So we can get different values of B field across the air gap just by increasing the LG1, LG2, increasing the effective air gap length that we have. Right? So as we go higher and higher, as the air gap length becomes bigger and bigger, we can get lower and lower magnetic field, making it have a sinusoidal shape profile as well. Alright, so this magnet is going to set up its own magnetic field in the air gap that's completely independent of the stator magnetic field. Alright, so there are two independent magnetic fields that are set up in the system. The first magnetic field is captured by the LM part, and hence the term magnetizing, because basically magnetizing the stator. Right, it's making the stator behave like a magnet, the LM term that we have there. Now we have a rotor which is setting up its own magnetic field, which is again sinusoidally distributed in the air gap, with its peak along this direction and then it's slightly reduced with the negative peak along this direction. Again, I'm drawn for a simple two-pole case here. Right? So then we figured out, what the EMF is going to be. We go back to the same expression. This term remains the same from the flux linkage derivation for the inductance. This phi B would now be replaced instead by phi of the rotor magnet. Right? That's all the difference is. The phi B came from that term right there. BA of theta instead of BB of theta, which would have been mu naught times PA divided by LG times I times cos of theta minus 2 pi by 3. And then once we know the magnetic field in the air gap, we can figure out magnetic field through any particular coil. Jonah gave the answer, right? Because you do integral B dot ds, whatever flux enters in will be the same as the flux leaving out, which is the part we derived here. This would be the same, and then we figure out the flux linkage. You go through this exact same process, But now instead of B of theta, B field's magnetic field, use the rotor magnetic field, which has exactly the same profile. Just instead of the mu naught NSP divided by LG times I, you have this BR factor. Alright, so that's all the derivation will be very simple. Just follow the procedure and you'll be able to get the same expression that I have right here. So we got, you will end up with this particular expression where the EMF is proportional to the strength of the rotor magnetic field, which again is expected because in that case the flux was proportional to the current. Here the magnet is already there, you don't need currents to establish the magnetic field, times the speed at which the rotor is rotating, which is again expected because when you have your flux linkage term, you have the sign of alpha term that comes about when you differentiate sign of alpha, you'll get d alpha by dt, which is the omega mech term that will come out. And then finally, this term is basically the angle between the A phase coil and the rotor magnet, and this is the way I've chosen it. Just because the derivation, it will be nice if it came out positive. I've chosen it in such a way that we are measuring the alpha in the opposite direction. Alright, but the magnetic field itself here in this diagram, it's rotating in the anti-clockwise direction because initially the A phase current would be at its peak. So the B field will be aligned along this direction. Then the B phase will be at its peak. So the B field will rotate and then come to C field. C phase and then come back to A phase. Right? So here it's rotating in the anti-clockwise direction and the angle is measured as positive in the anti-clockwise direction. In this diagram, just to keep the derivation simple, I am measuring the angle alpha in the clockwise direction. Right? So basically alpha is just negative of this theta that I have with theta. Right? That will come to picture when we model it. I have uploaded a Simulink model for this motor. When you go and look at the Simulink model, there will be a negative sign there. Don't be confused by it. Right, so we can do the same for the B phase, same for the C phase, which I've left as homework. The only thing that will change is the B phase EMF would be phase shifted by 2 pi by 3. C phase EMF would be phase shifted by 4 pi by 3. Right? So this is because of the rotor rotating. When the rotor rotates, there is going to be a changing magnetic field in the area because the rotor magnetic field is varying. And that varying magnetic field is going to link with the stable coil, which is then going to create an EMF, which is given by this term. Right, so we have this EMF term come into picture, and that we are going to capture with the voltage source. So this is EA, EB, EC. What is the frequency of this EMF? Is it the same as the applied grid frequency, omega g? No. What will be the frequency? Finish.
110.
1/10. Why is it 1/10?
Because our motor is spinning at a slower speed than the electrical part of the circuit.
But I didn't mention anything about the speed at which the motor is spinning. And in case of a synchronous motor, the 1/10 rule comes from the control aspects of it. Right? There is nothing such here. We are not doing any control just yet. We are applying some grid frequency and the motor starts to spin and then it keeps spinning. And at steady state, it has to reach synchronous speed. Right? Once it reaches synchronous speed, okay, let's start with a simple case. Once it reaches synchronous speed, what will be this frequency? Would it be same as the grid frequency?
If there's two poles,
If there are more number of poles,
then no.
why not?
It's based on the mechanical speed, and the mechanical speed could be slower.
So this term right there, right? So you have P by 2 times omega mechanical. So when you have this rotor, how did we figure out this equation that we have right here? We basically, so let's say we have a 4-pole case. So we have a north pole, south pole, north pole, south pole. In this case, and let's say I have some coil here, which is the A-phase coil, and I'm measuring the voltage across this. If this motor does a full turn, how many sine waves would the EMF across this would produce? If this rotor completes a full 360-degree turns, what will be the number of sine waves that are created?
Would it be 2
2. Perfect. Thank you. You would end up with 2 sine waves because at starting this is north pole and then later, half a degree, quarter turn later, it becomes south pole. So it'll go from positive, come back to 0, and then when it comes to this, it'll do the other quarter, and then goes from here to here and do the other quarter, and comes back from here to here, it'll do the other quarter. Right? So the mechanical rotation was omega mech. But the electrical change was 2 times omega mech. In case of a 4-pole motor. In case of any general system, there will be P by 2 times omega mech. Right? So the EMF would end up matching whatever, it will end up being P by 2 times omega mech. So for if you start off with a 60 Hz sine wave, as your grid voltage at steady state, the mechanical speed would come out to be 60 times P by 2 times 2 pi to convert to radians per second. But for a 4-pole motor, that would end up being equivalent to 30 times 2 pi radians per second. Right? That will be the mechanical speed. But if you look at the electrical frequency, that this term and this term would end up cancelling it out. 2 by p times. And then when you go back from the mechanical speed to the electrical frequency, you'll get the p by 2 times, 2 by p times, those terms cancelling out, you'll end up with the same electrical frequency again. So the back EMF would have to be the same frequency as your grid frequency at steady state. Because that's the only way an AC circuit can reach steady state, right? If the frequencies of all the voltages and all the currents involved are the same. If the frequencies are different, there is no steady state for an AC circuit. Right? That's the primary requirement for steady state. Right? So this frequency at steady state would be same as omega g. At other frequencies, what will the DMF be when the rotor is rotating, not rotating? What will the EMF term be? 0, perfect. If it's not rotating, d phi by dt is not changing. It will be 0. Once it starts rotating, you'll have some magnitude, and the frequency would be dependent on that omega m that I've written, the p by 2 times omega mech. Right? So this frequency would be completely different from this frequency in transient, but at steady state, they would start to converge and go to the same value. So everybody clear on this part? Getting the EMF portion. Right, so each of those 3 coils will create their own EMF, phase shifted by 2 pi by 3, 4 pi by 3, and whatever that other value is. Okay, so again here this EMF is generated for one single coil, one single pole pair. If I had 4 pole, let's say, how will I change this if I connect all of those in series? What will be the net EMF? What do I need to modify in this expression to get the net EMF if all of those coils are connected in series? That is the EMF of a single pole pair. If all of those pole pairs are connected up in series, what will be the total EMF?
Multiply by P.
Oh,
Multiply by P.
multiply by P or P by 2?
P by 2.
P by 2, because this is the net EMF for every pole pair. P by 2. Okay, what will I do if I have to connect them up in parallel?
Divide by P by 2.
Is it divide by P by 2? Anybody else?
Multiply by 2 by P.
Multiply, we already did that multiply by 2 by. Oh. So divide by 2, P by 2 is same as multiply by 2 by P. Right? But is it multiply by 2 by P? Again, don't link it back to the inductance equation. Because in inductance, when you connect these up in parallel or connect them up in series, the inductance changes. But think of these, each of these are EMF as a voltage source. If I give you a voltage source of 5 volts, 5 volts, 5 volts, and I ask you to connect them up in series, the effective voltage will be 15 volts. If I give you 5 volts, 5 volts, 5 volts, and ask you to connect them up in parallel, what will be the effective voltage? Just 5 volts. Right? So there is no P by 2 factor there when you parallel up the EMFs together. Alright, so again, here when the inductance, when you parallel them up, you'll have that divided by 2 P by 2 factor. That's how you end up with multiply by 2 by P, whichever answer will give or I will give, both are correct. But that's for the inductance, not for the voltage source. So you have to be quite careful when you do that for the voltage source, that you don't end up multiplying by P by 2 when you parallel them up. These are voltage sources. Okay, so let's come to the current derivation, sorry, torque derivation. Everybody clear on the EMF part? Okay.
When you're doing the series use, multiply by the factor and then still add EA, like the EMF from B and the EMF from C? Or is it just because they're the parallel like combination in there, and then for EA you multiply by the additional factor?
Oh, just for the EA. So when you don't add these EA, EB, ECs together,
Okay.
right? Because those are 3 separate voltage sources that are present in an equivalent circuit. Alright, these are completely independent 3 voltage sources. Within each of the A phase, it could have multiple poles which cannot be connected however you want.
Okay.
right? So those, depending on the connection, if you connect them up in series, you add them up. If you connect them up in parallel, you just retain the same way. But these three are completely independent voltage sources. They do not, merge or do anything. Like we'll combine them into per phase later, but for now they are just three independent sources.
Thank you.
Okay. Any other questions?
So like, for the homework questions, when it says like 6-pole 3-phase, does that mean that there's 3 phases per pole pair? Like,
The phase is independent of the poles.
Okay.
Right? The motor is either a three-phase motor. The homework I've given three-phase motor, two-phase motor, both considerations. The phase is completely independent of the poles. You can have a three-phase motor. So let's look at a simple case of a. So let's say we have a three-phase motor. This is a three-phase motor with two poles. This is what it will look like. Right? Equivalent when you draw it. So A phase, B phase, C phase. If I want to draw the same thing for a four-pole motor, the way I would draw it is A phase for the pole 1, and then the B phase for the pole 1 would be 60° away. B phase for pole 1, and then C phase for pole 1. Okay? And then I'll do the same thing again, repeat the motor again. A phase for pole 2, B phase for pole 2, C phase for pole 2. Now I have the option whether I want to connect this A phase for pole 1 in series with A phase for pole 2, or if I want to connect this 2 in parallel. Right? So these are completely different things. So just for simplicity, I'm drawing this diagram, but when you have higher poles, this is effectively what it looks like, because if you remember, the winding went from like positive to negative within one half of the motor for a 4-pole, and then negative to positive. That is the other set of winding. You have the option of connecting the top set and the bottom set in parallel or in series.
so like a 6-pole here, just P would be 6. And like,
Yeah, 6-pole B would be 6.
Okay.
And basically this would now compress this further within whatever angle that comes out to, and then you have two more set of these within the motor. Any other questions? So then we went on to derive the torque. So this I'm not going to repeat it again because we did a very detailed derivation. But a couple of things that we want to notice here. This current, when I derived it, that is for the current in the coil. Current in a pole pair coil. If I connect the windings in series, what will be the net current? What is the relationship between the current going into the A phase winding of the motor compared to the current in each of the coil of the A phase pole pair? If I were to connect those coils up in series,
the same.
it will be the same. So this is going to be equal to the current in the A phase winding A, terminal current, terminal A phase side, if we connect in series. If I connect them in parallel, what will be the relationship between the current in each of the coil compared to the current going into the motor terminal? Yeah.
Some of them would equal the current going in.
Okay. So if I were to connect them in parallel, this current would be equal to IA times 2 by P, where if I connect it in parallel. Right? So because if I have 2 by P by 2 times the whole pair is P by 2, if I multiply this by P by 2, I'll end up getting the total current IA, which is the terminal current. So each of these coils would carry a current of just 2 by P times whatever the terminal current coming into the motor is. So if we go back, these two expressions initially look, the tau A coefficient and the E coefficient looks a little bit different because of this 2 by P terms. But they do end up cancelling out in such a way that the Ke, Kt constants would still be the same for both the motors. Right? Because in this case, if I were to connect them up in series, you would multiply by P by 2 and this 2 by P and P by 2 would get cancelled. Going back here, if I connect it up in series, this IA is same as IA, so there is no P by 2, 2 by P factor outside. Coming back here, if I connect them up in parallel, the voltages are going to be the same, nothing modifies, it's going to be 2 by P. Coming back here, if I connect the conductors in coil parallel, the current splits as a factor of 2 by P into each coil. So I get the 2 by P factor here, which is again here. Alright, so if you do the model correctly and effectively your KE value comes out different from KT, then you have done something wrong in your pole count assumption. So irrespective of what you choose, the pole counts would come up in such a way that the values will come up in such a way that the KE effective, this term times this term, let's call it KE, and this term times whatever we have here, this factor, that KT should be the same irrespective of how you do the motor, right? Can I just a second, Jerome. Can anyone tell me an intuitive reason for why KE has to be equal to KT? Think of it in a simple DC motor case. Why did KE there have to be equal to KT? Well, basically satisfying power balance, right? Because the total power going into the motor, the electrical power, was the back EMF times the current. And the power going out of the motor was the electromagnetic torque times the mechanical speed omega. If I substitute this with Ke times omega, this expression becomes Ke omega times I. If I substitute this with Kt times I, this expression becomes Kt omega times I. This two power has to be equal. Right? So Ke had to be equal to Kt in that case. We did it through derivation and thankfully it did come out that Ke and Kt ended up being the same. Otherwise it would have been big trouble, we couldn't have accounted for the power. But again, this is an easy way of just showing it. Same thing happens here as well. We have some current going into the back EMF at some angle alpha, so the power would be E times I times sine of alpha, right? And then that has to be equal to whatever this tau times omega comes out to be. So if Kt increases, then Ke has to increase by the same factor so that the power is balanced in this case as well, right?
Yeah, sorry, I'm just a bit confused about how you'd connect the coils in series, like physically, or maybe that diagram doesn't like represent it, but.
Give me like 5 minutes. Well, towards the end of the lecture, when I'll open the slides for the 4-pole motor and I'll show the winding diagram that how you'll connect them up.
But does that drawing you drew like?
Oh no, these are not connected. Like these are,
okay.
Yeah, this is a separate set of coils. This is a separate set of coils. Separate.
Okay.
Right, and then the way you would connect them is like basically connect these two together and get these terminals out. That will be connected in series. If you're doing it in parallel, connect these two together, bring it as one terminal. These two together, bring it as other terminal.
Okay, that makes sense. Thank you.
Any other questions? Okay. So let's go back to our torque expression right here. This alpha is basically our mechanical rotation scaled by a factor of P by 2, right? And if the rotor is not rotating, that alpha is going to be a fixed term. What is going to be a torque? Will there be a torque if I just pass a current through the A-phase winding around? So let me delete all of these other ones and have some space here. So let's say I pass only current through the A-phase alone. Please be careful when you put parallel or series. I did ask both combinations in the homework just to confuse you, but think through it and get the correct answer. Right. So let's say the motor is not rotating. So omega m is equal to 0, which means alpha is some constant. What does my torque look like in this motor as a function of time? Assuming the voltages are varying like that. What I have given in the left is varying sinusoidally. What will my torque look like? Will it be a constant? Basically this I, right? I is going to be some Im cos omega t plus some angle. So the torque is going to vary. However, our current is varying. Okay? And this is going to have a net torque. So if you take the average tau net, that is going to be 0. In case of our permanent magnet synchronous motor with a single phase winding. Is there any way using a single phase winding can I get the motor to produce torque? Or let me rephrase it a different way. What would alpha have to be so that the net torque is not 0? We can go back to Fourier. What am I trying to get by net torque? Net torque is basically the area under this curve, right? If I do the integral of this curve that I get here, that is going to give my net torque divided by whatever time period I integrated, that's just a constant. So it's basically just area under this curve. So I have this function sine alpha, and then I have some other function cos omega t plus phi, and I'm going to integrate it over some time, over a cycle. What is the only combination that will give me a non-zero value? The only combination that will give me non-zero is if this frequency is same as that frequency. Right? Any other combinations, the integral or the inner product would end up being zero. That's exactly the property we exploited when we did Fourier transform, where we had some components of sines and cosines. To get to one particular sine component, we multiplied by the sine of the same frequency and integrated. All the other terms went to zero, leaving just that one final term alone. So the only term, the integral of this product and this product would be non-zero is that alpha is equal to omega t. Okay, so if alpha is equal to omega t, then this product, so let me work this. I'll do the cos again in a minute, but to start off, let's start off with the sine so that it's much clearer to see what's going on. So let's say this phi is 0, then you have sine omega t, which will give you sine square omega t. Right? That's the only time where the net torque would not be 0. So in this case, tau A. So tau A for this case would end up coming out to look like, right, with the frequency 2 omega t. Because this again, you can resolve it into sine omega t times sine omega t, just ends up being 1 minus cos 2 omega t divided by 2. Right? And that's the reason we have that offset 1 by 2, and then cos 2 omega t negative part, that's this other one being at twice the value. So it's just 1 by 2 cos omega t divided by 2. Right? Which is equal to sine omega t the whole square. Right? So now if I start to phase shift this, what is going to happen to this wave? Let's say this phase is no longer 0. How will this change? This product is something again you have seen in AC circuits. Right? When we figure out the power, the product of the current times the product of the voltage, that was the power. And we saw that if this is not aligned, in which case it will not be aligned if the load is inductive, not just purely resistive. Then we saw that this power term will start to move around as phi increases. This torque waveform is going to have some negative component, some positive component. Right? So the real power effectively came down in our AC circuits. In this case, the torque is going to effectively come down. In this case, right? When it becomes 0, this phase becomes 90 degree. Right? So if the phase becomes 90 degree, you would end up with product of cos times sine, which would end up having equal area on the top, equal area on the bottom, with the net torque being 0. Alright, so let's go back to our original equation. Cos of omega t. Right? So for the maximum torque to be achieved in both the cases, you would have to have alpha equal to omega t plus 90 degree. That will end up giving you cos omega t component. Right? So it needs to be phase shifted by 90 degree so that you can get the maximum torque. In other cases, you will get non-maximum torque. So once you get a permanent magnet synchronous motor, one-phase permanent magnet synchronous motor rotating, you can continue producing torque because there is a net average torque. So the problem is to get it rotating. If alpha, this alpha term is 0, or if this alpha term is some constant, then this was the torque. The average of this torque is 0. A one-phase permanent magnet synchronous motor cannot self-start on its own because the average torque across the motor is completely 0. This is one way of seeing it. The other way of seeing it is we have a magnetic field that's rotating in one direction, magnetic field that's rotating in the other direction. Right, going back to the experiment where we estimated the speed of sound, both these magnetic fields will pull the rotor magnet equally in both directions, effectively producing no torque. So either way you see it, you'll end up with the same answer that a one-phase permanent magnet synchronous motor cannot rotate. But once it starts rotating, you can produce torque in the motor and it will continue to rotate. What is the problem with this torque though? I don't think anybody would have ever seen a one-phase permanent magnet synchronous motor. I myself haven't seen. I've seen it used as a generator, but not as a motor. Why don't we want to use a one-phase permanent magnet synchronous motor?
Torque would oscillate.
Torque would oscillate because of this oscillation that we have there. This is then going to go into our transfer function 1 by fj plus b to create the speed omega. Right? And this oscillation is then going to cause oscillation in your speed, which is going to become very inefficient and quite loud. Right? When we go to induction motor, there is a way that we can reduce this oscillation because magnetic field is rotating in the opposite direction, that would encounter a lot of impedance compared to the magnetic field rotating in one direction, so that it would produce much lower currents and then would cause much lower torque. So in case of an induction motor, you can reduce the amount of oscillation. That's why you quite often find one-phase induction motors, but never a one-phase permanent magnet synchronous motor. Has anybody seen a one-phase generator, permanent magnet synchronous generator? Most of you might, without even realizing it. How many of you have been to Harbor Freight Tools? Right? So whenever you go there, they have this section for camping generator, right? Where it's just a one-phase single generator, where you put some generator and then there's a single-phase outlet that comes out of it. So it's basically a permanent magnet synchronous motor with the generator part coupled to the on the mechanical side, and then on the outlet is basically the A-phase terminal that's coming out. So the torque would be pulsating quite a bit in that case, but the way they get around it is having quite a large flywheel for the generator, so that the torque pulsation does not lead to speed pulsation. Because if you have pulsation at the speed, then your frequency is going to have a lot of pulsation as well, right? Because the frequency is directly related to your mechanical speed, and you don't want to have your frequency move around too much. But for camping power supply, that's absolutely okay, quite a good one, right? Even if the frequency goes from 55 Hertz to 65 Hertz, that's not the end of the world, but you can't do that for the grid. Okay. So now once we put all the three phase windings together, A phase, B phase and C phase, the net torque that we get is this expression. This again we derived last class. Now this is quite different from the expression that we have here. Here it was a product of sine of alpha cos of omega t plus alpha, or cos of omega t plus some phase shift phi in the current. Right? That is what this product term is what was creating the oscillation in the torque. But once you put all of the three phase coils together, and the net torque that comes out of it is this expression, where it comes in it doesn't come as a product, but it becomes sine of alpha plus omega t. Right? If you can get this alpha to rotate at the same frequency as omega t, then you get rid of that oscillation. So if your motor is rotating, let's say omega m is equal to whatever this grid frequency, omega gs, right? Then what is our alpha going to be? Alpha is just going to be integral of omega mt with a negative sign to it, negative of integral omega mt, assuming omega m to be constant, that's just negative omega mt, which is negative omega gt, right? So if you can get this to rotate at the same frequency as the speed at which the space vectors of the stator currents are rotating, then you can get a torque which is not pulsating, right? But what needs to be the angle? Would this create an effective torque? If this alpha was equal to negative omega gt, would there be a torque in the motor? No. What should be the angle? What would be the angle at which the torque is maximum? 90 degrees. So if you can get this to be at negative omega gt minus pi by 2, right, then you would end up getting your maximum amount of torque. Because this term would get cancelled out, what you're left with is pi by 2, and you'll end up with your maximum torque being generated. So let's try and visualize what's going on here. A lot of equations there. Let's put this all diagram. So this is the setup we have. We have A phase coil here, B phase coil here, C phase coil here, and the currents are some Im cos omega t in the A phase, Im cos omega t minus 2 pi by 3 in the B phase, Im cos omega t minus 4 pi by 3 in the C phase. At time t equal to 0, where will the current space vector be pointed? Comments? X-axis. So at time t equal to 0, this is where our current space vector is going to be. Again, you can plug all of this into the math and figure it out, but it's quite straightforward because at time t equal to 0, the IA phase current is at its maximum. IA, IB, IC. Phase vectors point to the direction in which the maxima is. Right? It's capturing, it's tracing the maximum value that you would get in the sinusoidal distributed case. So that's how we are trying to capture. At time t equal to 0 is going to be here. At time t equal to 120 degree, so at time t omega t equal to 120 degree, it is going to be along the B phase. In between is going to be going from A phase to B phase. Right? Okay, so where is the, if I want to plot the stator magnetic field due to the currents going into the magnetizing inductance, right? If there were currents going in the stator winding, there's going to be magnetic field in the air gap. The net magnetic field, what is the direction of that going to be? Due to the stator currents alone. Anybody? Which direction of the stator magnetic field at time t equal to 0 for the current profile given B?
Degrees from that.
90 degrees from that. Can you give me the reason? Oh, so at time t equal to 0, which of these three coils would have its maximum B field? A phase. So the B field of A phase is going to be at its maximum. And what did we say about space vector? What does the space vector point to? Maximum. It's going to point to the maximum B field, which is along this direction. PS space vector. Right? So or let me put it even clear, BMS. So the stator magnetizing field, established magnetic field. Okay, we know this before itself, because at time t equal to 0, current in the A phase is the maximum. Current in the B phase is going to be some negative half of it. C phase is going to be some negative half of it. And we already did this math as well. So we had some B here. And then due to B phase, it would have been negative 1 by 2B along this direction, 1 by 2B along this direction. The net sum of it again was 3 by 2 times B along the A phase direction. So whenever you have the current given to you, the magnetic field associated with the current is pretty straightforward. Because the flux established is directly related to the current, right? Lambda is directly just a function of current. L times the current, the A phase current, the B phase, C phase, whatever, or corresponding some element. Right? So if the current is in one direction, the flux linkage is going to be in the same direction. The B field associated is also going to be in the same direction. Okay. Where is the rotor magnetic field going to be? Take a guess. Is there any particular value it has to be in? Absolutely not. Perfect, Lillian. So because the magnet can be anywhere, the rotor magnet is an independent thing, right? When I start the motor, this is rotating at whatever grid frequency, let's say, the magnet is just going to stay there without doing anything. So it is just going to stay here, while these fields are going to keep rotating circles around it. If this rotor is rotating at the same speed as this, then it will go along in the same space vector direction. So this can be at any angle. So the rotor magnetic field BR can be at any angle. Let's call it delta. There is a name for it, load angle. And we'll see in a minute why that's called load angle. Right? So this is where the rotor magnetic field is going to be if the rotor is rotating at the same speed as the stator. Alright, otherwise it can be at any particular place. Is there a particular choice of delta that will create maximum torque? I don't know who gave the answer for it, Jonah or Kirnesh, one of you gave the answer already. Right there on the right hand side of the board. Is there a particular choice of delta that will give me a maximum
90 degrees.
90 degrees? So if I were to have the delta at 90 degrees, coming from the negative pi by 2 term there, this is preferred orientation, delta equal to 90, preferred. Why is it preferred? Why do I want to put the rotor magnetic field 90 degrees from the stator magnetic field? What is the advantage do I get?
Current.
What was it?
Less current is
Less
required.
current, which in turn means
Less losses.
less losses. Right? So if I were to make the sine 90 degree, sine of the angle at 90 degree, if you go back to this torque expression, right? IM term there. So if I were to make this 90 degree, this term has become its maximum that it can be. Right? That has reached its maximum. So for a given amount of torque, if this is maximum, then I can reduce the current that needs to go in the coil to produce the torque. If the angle is anything other than 90 degree, let's say the angle is 30 degrees or 60 degrees, right? Then this value would give you a contributing factor of 1 by 2. My current has to be double. So compared to this case, Was this if my rotor angle was at? So this is my preferred case, but let's say my rotor angle was here. PR space vector and for delta equal to 60 degree. For this case and this case to produce the current in the same torque, if this current was Im, this current has to be 2 times Im. Right? Because cos of 60 would have, sine of 60 would have given you 1 by 2, and that 1 by 2 needs to be compensated by doubling the current. Right? So to produce the same torque, you would have to push more currents mean more losses right here. Is that the only source of loss? If I increase more, if I put more current, what happens to the magnetic field in the air gap? I deleted the equation. B of T2 was mu naught Ni NSP times I divided by Lg. So if I increase current, magnetic field in the air gap increases. Is there a problem? Why is it a problem?
Saturated.
Saturate. So we end up with more hysteretic losses, right? We are doing a bigger loop on the BH curve. So that again would be a bigger problem. So you want to minimize this current as much as possible. Where will my EMF space vector be? Let's say my BR is somewhere here. What direction will my BMS space vector point to?
B cross I or I cross B.
I cross B.
Oh, that's a wrap. My bad.
That will be the torque, right?
Yeah.
What is the relation? So the EMF is caused because of what? Is it because of BMS or BR? What is causing the EMF? Is it the rotor magnetic field or the stator magnetic field that caused the EMF? Rotor magnetic field, right? Because the voltage created due to the stator magnetic field is accounted in the inductance right here. The voltage created due to the rotor magnetic field is what is causing the EMF that we drew as a separate term here. Right? What is the relationship between the flux and the EMF?
Equals N by dt.
nd phi dt. So if you have a flux in one direction, what will be the direction of the EMF that comes out of the flux? Was it?
Is it in the same direction?
Is it in the same direction? If so, the EQ expression that Hannah gave is same as saying voltage equal to L di by dt. If your current space vector is along 0 degree, will the EMF, the voltage space vector across the inductance be in the same direction as well? Was it?
The opposite direction?
Is it opposite? What is the phase difference between the voltage and the current of inductor? 90 degree. So if you have an inductor coil, you have some current and it has some voltage across it, V equal to L di by dt. Right? Your current basically lags your voltage by an angle of 90 degree. We have the same relationship here. EMF equal to, there's a negative sign there, d phi by dt. Right? So if it was just d phi by dt, your EMF would lag your flux that caused it by an angle of 90 degree. The negative sign is just going to make it in the other direction, leading the EMF of the flux that caused it by an angle of positive 90 degree. So our EMF space vector, again, you can go through all the equations that I wrote, plug it into space vector transformation and do the math, and you'll end up exactly the same drawing I'm doing here. But it's far more easier to visually, intuitively come up with what's going on. Right? So the angle between the rotor magnetic field and the EMF is going to be 90 degree. Stator EMF space vector. Right? Now we have everything present. We have our current space vector, we have a BMS space vector. How do I figure out the grid voltage space vector? Where will that be? I have all the terms available right here. So what is the grid voltage going to be? It is going to be the EMF plus the voltage drop across the two inductors plus the voltage drop across the resistor. So basically I take the space vector, keep adding the other terms to it. What will be the direction of the voltage drop across the resistor? So would I add it along the ES space vector, horizontal or vertical?
Direction.
Along the current direction, perfect. So the current direction is like this. So this is going to be our IS times RS drop. What will be the drop across the inductances? What will be the direction for them? Vertical, horizontal, or along ES? Yep, Lily.
It would be shifted by 90 degrees from the ISRS, right?
Okay. Going back to the same expression, right? So it will be phase shifted by 90 degree. So we have I S times Ln plus Ls. Again, these are space vectors, right? So the net voltage, so let me draw it a little bit big. Again, this should be times 2 times the times the omega electrical, right? Whatever the frequency that we have there, that is going to be your impedance. So the net voltage space vector is going to be the sum of ES plus ISRS plus IS times LS plus LS times omega E, and this space vector is going to be a voltage space vector, which is the total one that will come out of it. So this will be the answer to your final question. Basically, this is a three-phase circuit, and this will end up being a space vector. Sum of all three would end up giving you a voltage space vector. Ideally, we want this at 90 degree, the EMF along the IS, and then the D would be very close to the back EMF. Right? Let me just take 3 more minutes. So this is my three-phase circuit. And typically when you have a three-phase circuit, you can go to per-phase equivalent circuit when the system has reached steady state. Because all I need to figure out, if I tell you the current in the A-phase winding, you can exactly tell me what the current in the B-phase and the C-phase winding are going to be. It's going to be phase shifted by 20 or 2 pi by 3, 4 pi by 3. Right? So at steady state, I don't need to draw all of these networks. I can just draw one phase alone and give you this the diagram, and you can figure out what the other values are going to be. So that's all this reduction is doing. Right? Going from three-phase system to one-phase system, but not one phase per phase, is only possible if there is steady state. If it's not there at steady state, if I give you the A-phase current, you can't tell me what the B and C phase current are going to be, because there's going to be an exponential component associated with as well, which you cannot determine by just knowing one phase current component. With that, let me just take 1 more minute to show you the presentation and then run the hardware. Those of you have to leave, that's absolutely fine. So, take a look at how the space vectors look like. Right, so the setup that we have is a motor that's already rotating at steady state at the synchronous speed, and then I'm applying a sudden load torque. So if you go to this diagram here, as soon as so initially it's rotating at 1200 RPM, and then as soon as I apply a load torque, the speed starts to dip. So this is exactly for the 6-pole case that I gave in the homework. The speed starts to reduce, exactly the answer that Lillian gave, because the energy has to come from the inertia, so the speed dips. And then when the speed dips, this is the angle between the stator magnetic field and the rotor magnetic field. When there is no load, both of these are going to be aligned because there is no region for power to go out, there is no torque. Right? So these both are exactly aligned. So the angle is initially 0. But once they apply load torque, there is going to be a lagging. The stator magnetic field is going to, the rotor magnetic field BR is going to start lagging the stator magnetic field. And then it oscillates, goes back and forth, and settles at a new angle. Right? So if you see BS and BR are perfectly aligned with one another at the beginning, as soon as I apply the load torque, you can see that the BR starts to lag behind. Right? And the speed starts to change, and this changing in speed is corresponding to the BR lagging behind. And then it will do that oscillation going back and forth, and then come back and settle at some particular value. What does it mean if BR is rotating ahead of BS? If the rotor magnetic field, let's say, is rotating ahead of the stator magnetic field, what's happening? Generator. So you can think of this as the stator and the rotor connected by like some spring, right? And as you apply more and more load on the rotor, the spring gets stretched out, and that's basically the angle increasing, right? And if it's going the other way around, where the rotor is going forward, the rotor is basically pulling the stator along behind. So that would be the generator case. So if this space vector moves ahead of it, it is going into generator case or regenerative case. Both of it being generated, power going from the rotor to the stator. Right? So this is the vector. So this is the case where we are looking at all the vectors. So if you look at this, if you look at BS and IS, they would always be aligned. ES would be 90 degree forward from the BR space vector, right? And the VS would be ES plus, you do all of those sum, that will be the effective VS space vector. Right? So if you fixate your eye on any two vectors, you'll see that IS, BS are always aligned. ES and BR are always 90 degree phase shifted. So this is the diagram that we need in the final answer. Again, of course, a screenshot of this at one particular time, you can't of course draw a time varying signal. With that, those of you interested to stay back, you can look at the hardware demo. Those of you have to leave, that's absolutely okay. Okay, so let's do a hardware. So we have a permanent magnet synchronous motor on the table here, and on the right is the DC motor. And the power of the permanent magnet synchronous motor in this case is like twice or thrice the DC motor. So you can see the difference because the brush takes a whole bunch of force in the motor. That's one of the biggest disadvantages of a DC motor. So there is a, so those of you who have done the lab, you must have done the, how many of you have done this lab, PMAC motor? Has anybody done it? Okay. The TA would have asked you to run the rotor in an experiment. What was the reason?
Don't know the initial delta.
Perfect. So initially we don't know where the rotor angle is because this encoder that I have, it doesn't provide absolute theta. It only, every time it rotates, it will provide a pulse. So that if you count the number of pulses, you can tell the speed at which it's rotating, right? But it doesn't tell you exactly what the initial angle is. But I need to know the initial location of the stator current space vector so that then I can make sure that the load, I can figure out where the rotor position is and then figure out where the rotor is compared to the stator. So to do that, what we do is we initially give a small pulse voltage. We start the A phase with some voltage and then make the voltage 0. So if you pass current in the A phase and then pass no, apply no voltage across the B and the C phase, what will be the direction at which the rotor magnet will align? So if there is a current going in the A phase coil and the B phase, C phase has no current, then what will be the direction in which the rotor would align? Along the A phase, because the rotor magnetic field is along the A phase axis. So your stator magnetic field. So the rotor would experience some torque, but not a sustained torque. It will experience a torque to bring it to align along the same direction after which there will be no torque. So that is what this part is doing. So let me take it, run that, and then we are going to be doing this thing called V by F, where I'll increase the frequency. You might hear a sudden twist, right? So rotor in it, and then V by F. So what I'm going to be doing is I'm going to gradually increase the frequency of the stator voltage, right? And then I'm going to apply a voltage proportional to the stator frequency. This is called V by F control. We'll take a look at this, why we are doing this when we learn induction motor. But for now, what I'm going to do is start gradually increase the frequency. Why am I not suddenly increasing the frequency to the rated value, which is for this motor 50 Hertz? What will happen if I directly apply a 50 Hertz signal to the stator? How is it?
Nothing.
Nothing. Why not?
The load isn't synchronous with it.
Perfect. So in our equation right there on the right, the tau net, if alpha is 0, then the net torque is sine omega t, which is just varying sinusoidally. So there will be no net torque and the rotor will not start rotating. So I need to start off with very low frequency so that the rotor alpha can catch up with whatever speed at which the stator space vector is rotating. Once it catches up, I can gradually keep on pushing it faster and faster, and the rotor will keep on catching up. And the rate at which I can increase that will be dependent on the inertia of the system. If the system inertia is too large, and I apply and I ramp up the frequency too fast, it won't be able to catch up. So it's a fine balance as to how fast I can increase it. So let's go ahead, run this, increase the frequency. And the speed should, so you can keep an eye on the speed here and the angle between the stator and the rotor at the delta. This one will be the angle, this one will be the mechanical speed. Right? So let me increase the frequency. Hopefully someone in the front can confirm. Jack, you can probably confirm it's rotating.
Yeah.
So now it's rotating at synchronous speed, everything is fine and balanced. Now I'm going to start adding the load torque. Right? So let's keep adding. As I keep adding, you should see that the delta theta, that term starts to increase. Right? But basically saying that the rotor is falling behind the stator. What speed is the rotor rotating? Is it in the same speed as the stator? BMS? Hannah, you're saying no, why not? At steady state. At steady state, they have to be the same, right? Otherwise, there is no torque in the system. The rotor would come to a stop. At steady state, the speed is the same. It's just that the rotor is slipping behind an angle, not in speed. That's quite important. In transient, the speed will reduce, but it will come back and settle down to the same synchronous speed. Okay, so going back to the animation, we started at 1200 RPM. At the end of the day, we settled back at 1200 RPM. That's the only option. So if I keep increasing this load torque, the delta would keep on increasing. Let me hurry this up a little bit. At any time, if I increase it to an extent where the delta theta goes above 90 degrees, the motor would come to a stop. Jack can confirm its stop, and the omega make here also shows 0. If I bring the load torque back to 0, will the motor start to rotate again? No. Why not?
It's too high.
Frequency is too high. So I can reduce this load torque all the way back to 0. It really doesn't matter what I do. No matter what I do, the motor will not start rotating again. Right? So this is the biggest problem with the permanent magnet motor. When you connect to a grid, now this is okay because this has a current limit on the inverter, which can limit the current going through it. But as soon as the rotor comes to a stop, what happens to the EMF? EMF goes to 0. So you're applying this whole grid voltage across a tiny resistance and some tiny inductance. That's going to cause a huge amount of inrush current, which will either burn the coil or it will demagnetize the magnet, because you'll put a magnetic field so large in the opposite direction depending on the rotor alignment that you can completely demagnetize the magnet. Right? With that, we are done with permanent magnet synchronous motor. On Friday, we'll start with induction motor.